Good day everyone, welcome back to my channel for Motec Monday. In today's episode we're going to be discussing aerodynamics. So this is a topic that I've been wanting to cover for a long time, and I think that a lot of other viewers are going to be interested too, because this is something that maybe a lot of people thought wasn't possible to do in iRacing, and I have my BMW Z4 to talk and help me illustrate. But aerodynamics are obviously very important in racing, and I think we all know that. But the challenge was, how do we use that in iRacing to help us out? You may be racing in Formula 1, but there are a lot of other cars that will benefit from some of the stuff that we're going to be talking about today. So, what are the things that we can adjust in the car to adjust our aero and, the setup and the performance of the car? Well, you can adjust the wings, right? Wrong. Turns out that the ride height has a tremendous amount of effect on the car's aerodynamics, because the entire car is in fact a wing. So every time that you make an adjustment to the ride height, you change the pitch, you're still changing the rear wing angle. So in fact, it's possible for you to maybe increase your rake, bring down the nose more, or bring up the rear. You're adding rear wing. If you're in a case where you had it was really cold air, really high density of air, and you actually had really long straightaways, if that was a case where you had to make a rear ride height change for the fact that maybe perhaps you needed more rear roll or something like that for mechanical grip, you would want to bring down your rear wing, because as you increase the pitch, that wing angle changes. You're also changing in the rear diffuser of the car, its effectiveness as well, and with the aerodynamics of the underbody of the car, you're also changing the center of pressure along the bottom of the car as well. So here you have your front splitter, and as that gets closer to the ground, that increases its effectiveness. It increases the rear diffuser's effectiveness, and like I said, you'll change the center of pressure with any kind of ride height change. So teams spend a lot of time talking about their ride heights, and they study them, and what they do is they basically look at ride height sensitivities, which is how is the car's aerodynamics going to be affected by changes in ride height. If you're racing in GT, then usually mechanical grip is going to be a first and foremost driving factor, or at least that's the state of affairs at the moment, and perhaps in the future that'll change. It used to be maybe like in the early 2000s, late 90s, mechanical grip was obviously number one by far, and the cars made nowhere near as much downforce as they do today. But today it's still a case where mechanical grip will probably be the first thing that you're going to set up, and then after that you're going to want to see where your aero is. But if you need to make a sacrifice, you need to have your ride height set up for mechanical reasons and have your roll gradient set up properly, and then after that, then see where that puts you aerodynamically. But then if you're having issues in fast corners, then that's where that compromise comes in, and then you may need a compromise and make a change to either the rear wing, the splitter, if you have that option to make an adjustment for, or the heights. And you'll see that the changes actually turn out to be very effective. That's why teams do a lot of testing, and then they'll construct what's called an aero map that'll list out all the sensitivities. And then obviously you have cars like Formula 1 cars where it's all about aerodynamics, and they pretty much will set up the car's heights and everything to be optimal for aero purposes, not for mechanical grip. So first, let's start off with the math, because that was the most challenging part of this process. Let's get off our ass and do some math. So here we are. So these are the governing equations that we're going to be working with. This is for the force of lift. What is it a function of? Well, lift is a function of the air density, which is rho, the velocity of the car squared, and this is the coefficient of lift, and this is the frontal, This term right here is the frontal area of the car. So let's see. So this is obviously the side. Let's see if we can get a side image. This is the frontal area of the car. So basically what you would do is calculate the area of the front windshield, the rear wing, mirrors, the nose, all of that. That's the front area of the car. And that's it. That's pretty much it. Same thing for drag. Now, what's important here is these coefficients, CL and CD. The coefficient of lift and the coefficient of drag. And what they're going to do, they're dimensionless, unitless numbers, and they are kind of like the adjustment factor that helps calculate the force correctly. They're consistent, they're constant. But they are dependent on the area of the car, the speed that the car is going at, and the air density. So how are we going to use these? Well, we're going to rearrange some of these terms, because what we want to calculate is the coefficient of lift. So these are the equations that we're going to be working with. So we're going to rearrange these terms, and then we're going to calculate for the coefficient of lift times the area and the coefficient of drag times the area. The reason that we're going to do that is because we don't actually want to calculate the area of the car, and we also want to make it a little bit more comparable between cars. So CLA is actually something that's kind of standard to do, but this makes it independent of the area. And it kind of helps us out, so we don't have to bother calculating the area for all the cars. We'll just make it a function of the area and leave it that way. And what we'll do is we're going to just take the force of downforce on the car divided by 1/2 rho v squared, which we're going to call the dynamic pressure. So this is going to be a channel that we're going to make by itself that will be 1/2 rho v squared. And then we're going to calculate the load, the vertical load on the front of the car and the rear. This is load front, load rear. And similarly, we're going to do this for the drag as well. We're going to, you'll see the dynamic pressure term, and then you'll see the mass. Will be the mass of the car in kilograms. G long will be our longitudinal acceleration, and G will be the standard acceleration due to gravity. And this is just basically a conversion factor because G long is in units of G, and this multiplying it by 9.81 meters per second squared will make it back to its SI units, and then that'll give us the correct force. So those will be our two main equations. So from there we're going to have to calculate what the loads are in the front. The drag is actually a pretty straightforward calculation. We know the mass, we know the G long, obviously that's something that we work with all the time. So you can almost calculate that right away. So here are the equations for the load front that we have to insert into this function here. The main one that you'll notice that's really important is MR, and you might ask, what's that? MR is the motion ratio of the suspension. So we're basically going to be calculating downforce at the damper, and that's where I guess our suspension position sensors, wherever that's located. And we're going to need a motion ratio because in some cases, for some cars, the amount of movement in the damper is not one-to-one. It's not in a one-to-one relationship to the movement of the actual car body. So your ride height would sometimes change more or less than what your actual damper is moving. That's obviously done on purpose, but we need to take that into account because you will then overestimate your downforce if you stick it without the motion ratio. So a very important term. We need to know the motion ratio of the suspension relative to the car's body motion. KF will be the spring rate in the front, which is easily known and given to us. Then we have delta X left front plus delta X right front. That is our spring travel. 1, suspension travel. Let's call it suspension travel. And what that does, that's just using Hooke's law. We're gonna calculate the force on the springs due to weight transfer. So then, what is that? That's the spring rate times final position minus the initial position. So we always know what the suspension position is of the car. That's easily given to us. But what we need to find out is the zero position. So we'll have to calculate what the zero position of the suspension is, so that we can subtract how much the suspension traveled. But that's the suspension travel added for the two front springs, because there are two springs in series. No, well, they're parallel. Sorry, two parallel springs, the left front and the right front, and springs in parallel are additive. So we'll do it this way. And then this term right here is mass, G long, conversion factor, the height of the center of gravity, times divided by the wheelbase. These two equations will give you the load on the front tires and the load on the rear tires. You'll notice that there's a difference here of negative sign, so it's a change. Like this gains with a positive G, and then if G long is negative, then that'll switch here, and then it'll subtract. Anyway, this term, in the case of if you are at constant velocity, will be what? Well, this will be zero. This will go away because G long will be zero, in which case then that means that if we're doing straight line constant speed runs, all we need is this term, and we don't need to bother this term. The other thing is that this is also going to be useful, like if you wanted to calculate load on the front and the rear, to calculate maybe roll transfer rates, and which is our weight transfer. And this also lets you see, gives you a little bit of insight as to how weight transfer works. But you'll see that there are two terms here, and in fact there are three types of weight transfer. And this one is independent of suspension movement. This is a geometric weight transfer, and it is only dependent on acceleration, and that's the only variable that's changing in time. All the other ones are constant. And what that means is that this is an instantaneous weight transfer that happens independent of the suspension movement and body roll and pitch, and it's always there. So as soon as you hit the brakes or hit the gas, this term and its weight transfer happens instantaneously. This one, however, in the first 1/1,000,000th of a second of time that you've applied the brakes will be zero, because the suspension hasn't compressed yet, and will increase in time until you peak. There is no other way around it. That is how this function works. So for you to develop that load on the front and increase it, the suspension has to reach its steady state point once this delta X has reached its maximum and stops changing. So that's weight transfer, and you can see how it's actually made up of, in this case, two terms. There is also another term for unsprung mass. There's a weight transfer of the sprung mass. There's weight transfer for the unsprung mass and the geometric weight transfer, and they are all added together. Two of those are instantaneous. One of them is directly proportional to the amount of suspension travel. Very important. And I have a couple more equations. Let's see. And we're going to do the force of the rolling drag. So that'll be mass G long G, and that's just going to be taken at a different speed. So let's go to Motec. Okay, so we're here in Motec. We want to make a few channels for these things that we talked about. Let's see what they look like. I made a lot of channels. I made my own aero math here. Remember, this is an advanced tutorial. If some of the math and the creation of these math functions are a little bit difficult to understand, I strongly suggest you just go back to the beginning tutorials where we kind of hold hands and I walk you through the process entirely. But this is a very advanced tutorial. So let's just talk about, I guess, what the plan. The plan is that we're going to do straight line. We're going to do some straight line testing, and we're going to do it at a couple different speeds. What we need to do is first find that zero suspension position. There is an issue with suspension position in iRacing because when you get the car dropped, or you look at your ride heights, when you are at zero speed, easily I could obviously just stop the car at any point, and that would work just fine. But you can't, because the car kind of does some funny little thing where when it's at zero velocity, it kind of like falls. Like here, it goes down. Like you can see the suspension is at 67.3 millimeters, and then at some point here I start moving, and it actually, I suppose, the car gets a tiny bit higher, and then I start accelerating, and then it goes all over the place. But we can't use this as our zero position because it will cause a little bit higher error than is necessary. So what we need to do is we need to find a speed that we can zero the suspension. So we're going to do that at 60 kilometers an hour, and we're going to hold a constant speed. So we're going to go out testing. I did some testing already at Daytona. So down the back straightaway on the apron where the track is flat, I held 60 miles per hour or 60 kilometers per hour for a few seconds. That's going to be our zeroing place. We're going to zero our suspension there. We're also going to zero or just check on a couple other little parameters, perhaps the rolling drag. No, we're not going to do rolling drag at 60 actually, but we're basically just going to zero the suspension at 60 kilometers per hour. Then after that, then we're going to do our aero test. We're going to speed up to 150 kilometers an hour. 60 because there really shouldn't be any aerodynamic load on the front of the car or the rear at 60. So if we assume that the aero is negligible at that point, then that means that we can assume that the suspension is as high as it should be. We're at constant velocity, so we'll zero it there. Then we'll speed up to 150. Then we'll hold that for a few seconds. And then after that, I'll speed up again, bring it down to 150, just so I can have an even, a really easy way to tell on the telemetry where I'm at. And then I'll do a coast down test where I'll push into clutch and just coast down to almost 0 miles per hour, or yeah. And then from the coast down test, we'll get our coefficient of drag and our coefficient of, just the coefficient of drag and our rolling friction. Coefficient of drag will be taken at basically between 150 and 140 kilometers per hour or thereabout, right at the peak aerodynamic drag, which is at the highest speed. And then we'll take the rolling drag as the car is coming to a stop and there is no aerodynamic load. And you know that the only thing that's actually acting on the car to slow it down is the internal friction of the components, rolling drag of the tires, and things of that nature. So like the bearings, brake discs, they're slightly touching the brake rotors, a little bit of the friction on the tires. That's it. Hysteresis. So I'm going to do more of the testing, but let's look at, so like I said, you have to zero the suspension. So let's see how we did that. Here it is. So you have to do, and then you have to make it a constant value. So this is, so I made a channel called suspension zero front, statistical mean, and then we obviously have to use our choose function. And what did I do? So I said choose between the speed of greater than 58 and ground speed less than 62. So that gives us a 4 kilometer per hour buffer zone. And this is just to make sure that you're going straight, so that you can do this at any racetrack. But to make sure the steering wheel is held straight, I put a lateral limit on the G-force. You can also change this to absolute value if you don't want to do this twice. Yeah, it is. So it's absolute value of the lateral G-force and make sure that's less than 0.2 Gs, which is a huge actual margin. I should lower this. This could actually be around 0.5. 0.5, 0.05, and then that's going to tell me what comma, and then suspension position of the front plus the suspension position of the rear averaged, so that's divided by 2, and then otherwise return invalid. So that's going to give me a good average. That's going to give me a good average for the suspension. So then that's how you calculate the zero suspension. So what does this look like when you look at it? Oh, well, I have it averaged. Let's look at it. Let's take away the stat mean for a moment. Oh, hit the wrong one. So here was my testing zone, and you can see it eliminated everything else. And just at the different points where I'm running at 60 kilometers per hour, you can see that's where the suspension 0 comes in, and at no point else. I must have crossed over here at some point and did it again. And did it again. So I did several laps where I was doing the same procedure where I would hold 60, then accelerate to 150 and hold that speed. So you see how it works. Pretty cool. We'll bring back the stat mean so it'll work properly. Now it should just be a constant value. So now it's 69.08 millimeters, and that is our 0 position for the suspension. From there, we needed to calculate the motion ratio. So motion ratio I have here, MR front, and the motion ratio again is just calculated at the speed of 60. So that's the other thing that I was calculating at 60 kilometers per hour, which was the motion ratio. So that's going to take the right height and divide it by the suspension position, and then that gives us our motion ratio. And they did come out correct, because I have been comparing this data to some real life data that I have access to, and the numbers do come out very reasonable. So let's see, like MR. Let's collect these two. And motion ratio in the front is 0.65. The motion ratio in the rear is 0.46. Those are, reasonable numbers. I would love to know if that is actually correct for the BMW Z4, but they are definitely in the ballpark for what a real race car would have. So we calculated those two values at 60. Then we went on and had to calculate the downforce. So I have my downforce calculations here, and you can see a lot more went into this one. This is 155 to 145, and then again I took out a lot of the stuff to make sure that I'm dumping a lot of data to make sure that we're getting good data, so the car's not turning, even a limit on vertical G, to make sure that we're in a limit and we're not in a track that's too bumpy or surfaces that are too bumpy, or otherwise we throw away that data. And this is a motion ratio times the spring rate times the suspension travel, which are two channels that I had made for that. And then we smooth that out a little bit. And then we're gonna, this is not averaged yet. I did create a different one that was going to be mean downforce. That gives us the static number that doesn't change with time. So we did that. Same thing, calculated the drag I made a constant for the gravity. So for this one checks the drag. It's going to be for when the car is on the coast down test. So then the clutch position, make sure that's at 0, throttle position 0, brake position 0. And if that's true and the speed is between 150 and right now I have it set to 75, then we can calculate, which is the car mass times g long times gravity times and then that's subtracted from the rolling drag, and then that's all divided by the dynamic pressure. So let's see what this looks like. Let's go ahead and I'm going to do another run real quick. I'm going to change the wing angle and we'll see if we can do a comparison and see what that does. Okay, so we're now back from my run and we'll see what the results come in as. So here you're going to be able to see this is the entire run that I did. I changed the downforce and I put a much higher rear wing on the car, the maximum actually. And let's see what we did. So here, we started at 0. Right now I have it on time. So we're at 0, then I sped up and found the back straightaway, slowed down again, and held around 60 kilometers per hour for a little bit. Then I sped up to 150, held that for a little bit constant. Then I sped up again to go back down the back straightaway. Then 150 again, and then did a coast down. So this section is a coast down. Then sped up to get to the back straightaway again. Then held 150 for a few seconds, and then did another coast down. And then finally did a coast down where I slowed down to 0. Which was finally around here somewhere, and we're off the chart. But there you can see 0. So we have all the data that we need, and now my functions will do the rest because they will find those moments. As you can see here in the chart, in the graph, this is a case where the downforce was being calculated during our straight line runs. Like here, you can see the downforce pops up right here. Why? Because our G long is below the threshold, the G lateral is below the threshold. Here you can see that there's a gap in the information. Why? Well, let's see. More than likely it's the vertical G. It went to 102. I think the condition maybe is less than 1.02. So in that case it'll throw away the data. Right here, the G vertical is 0.98, and let's see what the condition is. So we're calculating G-force 98. So that means that if it's equal to 1.02 or 0.98, then it's going to throw it away. So that's the reason why there's a cut right here in the data, because of some bump created excessive vertical G-force. So that's good. So everything's working fine. And what are our results and what do they look like? I just have the plot here just to make sure that I'm checking on everything to make sure that it's working right. This is our car setup. So this is our front spring rate, our rear spring rate, the corner weights on the car. This is the static setting on the right heights. I have it symmetric, so right now I'm only listing the left front and the left rear, but that's both corners. And I put a wing of 10 on the car right now. And we calculated our motion ratio, 0.46, same as it was before, so that's good that that's staying constant. Rolling drag, 123 newtons. Mean front downforce, 917 newtons. Rear is 1,592 newtons. These are very reasonable numbers. And the Aerobalance, that means that there's 36.5% of the downforce over the front axle. At first I kind of thought that was a little bit strange, but in fact I compared data to other GT cars, and very often they will have more rear downforce than they do front. So then that reassured me. I'm like, oh, okay, I didn't know that this was the case, that we were in the ballpark. But we are getting more rear downforce than in the front. And again, this is with maximum wing, and our coefficient of drag is 1.46, and coefficient of lift is 2.33. The most useful number out of everything here is the downforce, the center of pressure, and basically, if you can see it, I mean, as you're changing the rear wing, you're shifting that center of pressure back, 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 back. So that's basically like the cousin of the center of gravity, but this is the center. Gravity is acting at a certain point. Once the car is set up, it's kind of like set in that location, and that's the center of, the weight transfer happens from. Every time that you're turning left and right, that it's all dependent on how the car moves is all dependent on the location of the center of gravity. But the center of pressure is obviously only acting at high speeds where the aerodynamics come into play, and that we shift with the wings. And sometimes you'll have a crossover where maybe you have a center of gravity that's pretty low, and maybe just a little bit more front, a little bit more forward. But then you'll have a center of pressure that's a little bit more further back, and your balance is not directly related. I mean, it's related to your center of gravity, but there's other factors that are also involved. But say that you have mechanical balance, or where you have more front grip than rear grip, and if you could put that as a percentage of based on front to rear, you could have it biased to the front, where you have a lot more mechanical grip in the front, but then you have your center of pressure way back. So then that means that you would have basically understeer condition in high-speed turns, and in low-speed turns you would have oversteer, which may or may not be a desirable quality, depends on the racetrack. So that's the case here. We have a lot of rear downforce, and these downforce numbers, again, are very reasonable compared to data that I have for older cars. That means that over the last decade and a half, quite a lot of progress was made with these GT3 race cars, which makes a lot of sense. So let's go ahead and compare it to a different setup. How do we do that? Okay, so this is a comparison between 10 and 2 rear wing. And you can see the difference. The coefficient of drag, that changed by almost 1/10 of a count of drag. The lift, that went down a little bit actually, which is not a surprise, which is, we're talking about downforce, not lift force. You can see it here just in plain numbers where the drag or the downforce went. So before 917 newtons in the front, that went to 1500, and then at the rear, that increased a little bit as well. The total downforce, the rear downforce went down. So we increased front downforce, the rear downforce went down, and the front percentage changed from 36 to 45. So it's interesting to see how that affects things. Now you can actually take this drag, and right now I don't have things set up in such a way that I could basically calculate what the speed difference would be. But with this, you could also just punch it into some equations, and you can find out what the actual top speed difference would be, because right now we're running at 150. The drag coefficient will still stay the same, more or less, and you could calculate what this means in miles per hour at the end of a straightaway and how much that's hurting you. We don't have it set up right now to calculate that. Right now, the biggest number that I wanted to know was the balance. So you can see that this is a considerable shift. The number 2 wing shifts the weight to, or the center of pressure forward, and you can see where maybe at 0 wing or a little bit negative, you might actually have a positive balance, where you have more downforce in the front of the car than at the rear. The other thing that will change is not only, like I said, the wing angle, but as well as the ride height. So that's going to be a video, the following video for the aerodynamics. We're going to take this a little bit further, and we're going to do some ride height runs, where we're going to be varying the ride height on the car, and then we're going to construct an aero map using the 3D table. So we're going to fill in values for ride heights here, dynamic ride heights, and fill in what the aero percentage was, or we're going to do the coefficient of drag and the coefficient of lift, and then we'll create a map of these values that will tell us where our downforce is relative to our ride height, which is actually the more critical thing. I mean, I think it's pretty obvious when you're making wing angle changes, but the changes in ride height and how they change your downforce is actually a little bit less easy to see, and we need to actually put some real numbers to it. So that's what we're going to do, not next week, but the following week. Next week I'm going to be touching on tires, because right now that's a really hot topic ever since iRacing did a couple updates last month for 2017 and season 2. So people have been talking a lot on the forum about finding the optimal tire pressure and tire temperatures, because apparently that's changed. So we're going to go ahead and try to find an analytical way of determining what the optimal pressure is and the optimal tire temperature is. We'll work on that next week, and then the following week we're gonna construct some aero maps, and we're gonna see how sensitive the cars are to ride height changes. Okay, so I hope you guys enjoyed the video and learned a lot. Remember to subscribe to my channel, and so that you can catch all these updates, and we'll keep on cranking out the math, and I'll see you on the track. So subscribe to my channel and have a good day.